Welcome back to Chem 101. In the previous videos we were looking at quantum numbers, using them to determine the types of subshells that we would find in each energy level. And before that we were looking at how to determine what quantum numbers we would have based on principal energy levels, which again can be related to the row that an element is in. So if none of this looks familiar to you, you probably want to watch some of the previous videos. What I've got here is the subject of today's lesson, which is electron configurations. And I've got two electron configurations shown. You can think of an electron configuration as the layout of where all of the electrons are, sort of address, as it were, though the set of 4 quantum numbers for each electron, which will be the subject of a further video, kind of more accurately describes electrons' address. But here you can see that the sulfur 2- ion has electrons all spaced out and filling up these energy levels. And when we are writing electron configurations, it's important to remember that when we fill up these shells, it's always from the ground up. And if you don't remember the order in which these electron orbitals fill, this can be a handy tool. So if you remember knowing what the value of n is, in terms of the first quantum number, we can determine what the value of L should be, and L will tell us what subshells we get. So when n is 2, we get an S and a P. When n is 3, we get an SP and a D, and so on. Now, if you list them out like this, and you sort of draw arrows through the diagonal, remembering to come back up to the previous top of each arrow, you will get this sequence. And this sequence never changes. Electrons will always go into the 5s after the 4p. They will always fill up the 6s before they go into the 4f. Now that's true when we're talking about ground state electrons. We can get electrons from low energy levels to jumping to higher energy levels, but that's not what we're talking about here. So electron configurations for ground state, we're going to look at how we determine them for ions, both positive and negative, and how we determine them for neutral atoms. And if you already noticed something about copper, we'll talk about that too. Stay tuned.
Alright, first things first, when we are writing electron configurations, we need to know what we're writing the electron configuration for. So let's pick something. Let's take sulfur 2-. So the first thing we want to do is total the number of electrons. Otherwise, what's the point? We need to know how many electrons we have. So look at the periodic table, see that sulfur has 16 electrons. Now this is sulfur 2-. So it has 2 more electrons than a normal sulfur. This guy's got 18 electrons. Now what we want to look at is how many electrons fit into each subshell. So the S can hold 2, the P can hold 6, the D holds 10, the F holds 14, the G holds 19, though we don't really need to get that far. So then we can come up to this electron configuration here and actually start writing in some numbers. So we'll say the 1s gets 2, 2s gets 2, we're just filling it up. 2p gets 6, 3s gets 2. How many are we adding? We're adding 18. We've gotten 12 so far. So 6 more, and they will all fit into this energy level, the 3p shell. So now we can finish and write the electron configuration for sulfur. And what we would write is 1s2, 2s2, 2p6, 3s2, 3p6. We're just taking the electrons that we filled in, the ones we filled in up here. Alright, let's pick something new, like gallium. Gallium has, if you look at the periodic table, it has 31 electrons. So we're just going to go through and fill in all of these electrons. So 2, 4, 10, 12, 18, 20. Now remember, the D shell can hold 10, so we're at 30. And gallium has one more electron, and that would go into the 4p orbital. So then we can write the electron configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p1. Alright, I think we're up for a challenge. Let's do platinum. Platinum has 78 electrons. Now platinum is going to be in the 6th row. It's a transition element. That means it's going to be after 6s, but before 6p. And so our final electrons will be ending up there. So let me go ahead and just start filling in all these electrons. We've got 2, 2, 6, 2, 6, 2, 10, 6, 2, 10, 6, 2. The F shell here has 14. And platinum is the 8th element in the transition series of this row, so it will get 8 electrons. And so if we were to write out now the whole electron configuration, it would look a little something like this. Alright, so that's a long configuration, but you can see that all we've done is fill in from the ground up, from the lowest energy to the highest energy. So if you know the sequence and you know how many electrons, you can't go wrong. Okay, so let me show you what happens if we ionize this. We did a negatively charged one. Let's do a positively charged one. So let's think about how we would write platinum, let's say platinum 2+. So if we wanted to show platinum 2+, we need to consider how many electrons it is. And when something ionizes to form a cation, it loses an electron. In this case, it loses 2. So we wouldn't have 78 electrons, we would only have 76 electrons. And if we were filling that up, the difference here would be that, the difference would be that instead of having FD8, we would have FD6. Now that's true when we're writing the electron configuration. Actually, no, that isn't true. That's not true at all. This is the point that I wanted to make. We actually would write this as, let's see if I can get it here, 6s0. Oops, that didn't work. 6s0, 5d8. Now you're probably wondering, why would we write it as that? Why wouldn't we write 6s, I'm just going to recreate bottom here, 5d, why wouldn't we write 5d6 if you lost 2 electrons? And the thing to note here is that when anything ionizes, it always loses its electrons from its highest energy level. And in this case, that means the energy level with the highest principal quantum number. And so even though the last electrons that we stuck in here were these 8 electrons in the D shell, the S electrons belong to a higher principal quantum energy level. And those are the electrons that are lost first. So whenever you're writing electron configurations for ions that are in the transition elements, or the transition series, you got to remember that they'll always lose their S shell electrons first. Alright, let's try this again just to emphasize the point. Let's do vanadium 3+. Now, you might be tempted to figure out that a vanadium 3+ would have 20 electrons and then try to just stick in 20 electrons. You shouldn't do it that way. Let's find the electron configuration for vanadium first, and then we'll worry about the 3+ part. Okay, you can see that after we stick in all 23 of vanadium's electrons, we end up with this electron configuration. Now that we have this electron configuration, For vanadium, then we worry about removing these 3 electrons. And remember, don't make the mistake of taking these 3 electrons away. These aren't the ones that are lost first. The 4s shell will lose these electrons first. So we would remove those 2 electrons, and we would put in a 0, and then we would put in, this had 3, so we would subtract 1, that leaves 2. So this would be the electron configuration for vanadium 3+. Remember, highest energy shell loses its electrons first. Now that you know about some electron configurations, let's look at some irregularities among them. So take, for example, these 2 elements, chromium and copper. They're both transition elements. They both have partially filled d shells, but notice that because chromium is only 1 electron away from having a half full d shell, and because copper is only 1 away from having a full d shell, that their actual electron configurations look slightly different. Their actual electron configurations favor having a half-full shell or a full shell at the expense of having a half-full S shell instead of a full S shell. So chromium and the elements underneath it in the periodic table, and copper and its elements underneath it in the periodic table, will all have these similar trends. When they're close to having a full or a half-full D shell, they will actually sacrifice having a full S shell. So bear that in mind when you're writing these. If you've made it this far through the video, you're probably wondering there's got to be an easier way to show these electron configurations. Some of them are pretty long. And you're right, there is an easier way. And we call that the condensed version. And it involves putting into brackets the noble gas that's preceding your particular element, whatever that happens to be, and then showing the electron configuration for just the valence electrons, or the highest principal energy level. So let's do an example. Let's take the electron configuration for potassium. Now potassium has 19 electrons, and in the long format we would write it as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but since everything up till 3p6 is basically the electron configuration for argon, we can simply write argon in brackets and then 4s2. And this will represent the electron configuration for potassium, the condensed form. So whenever you're trying to write the condensed form, remember that you can use this as long as you show the preceding noble gas and then the last row of the electron configuration.